Okay, so this might look a little different today. It feels very, very different. So this is math 265, rotated by pi over 2, minus pi over 2. Okay, so multivariable calculus today is December the 1st. Wow, we are almost done, aren't we? So last week, on Wednesday, before Thanksgiving, we wrote down how to integrate a vector field. And we finished by writing down what we'll write down again here, which is the fundamental theorem of line integrals. So I don't think we proved it before we left. Is that right? We stopped before giving a proof?
Yeah.
So maybe I'll give at least a little sketch of a proof. And then, after doing maybe a couple examples of this, we're going to talk about one of our first named theorems. When I say named theorems, I mean after a person that generalizes the fundamental theorem of calculus. Actually, the fundamental theorem of line integrals, this looks a lot like the fundamental theorem of calculus. And this is going to be even more so. But it has a real person's name attached to it, which is kind of cool. So we'll see what we can get to today. So let's just recall that if you have a vector field, capital F, and you have a curve C, smooth curve, and it's parameterized by the vector function, say, r of t, where t goes from a to b. And that we assume that f is continuous on C. And remember, continuous on C means that the components of the vector field are continuous on C. So then we define the line integral over C of the vector field. And the notation for that was f dot product dr. Okay, so this is the line integral of f over C. And the way you can compute this is you integrate from a to b. Then you take the vector field and you evaluate it at r of t. And then you take the dot product. So this is a vector field, right? Or a vector. So you take the dot product with the derivative, and this gives you a scalar function that you can integrate. Right? So if you take a vector field and you integrate it, or you take the dot product with this vector function, you're going to get a scalar function. And so then you can integrate with respect to t. So we wrote down this definition for the line integral. Excuse me. And then in the special case where we're looking at, say, a vector field over 2 or 3 dimensions, and if we assumed that f is some differentiable function, so we can take the gradient of it, for instance. And if we assumed that the gradient, nabla f, is continuous on C, then we were able to get the fundamental theorem of line integrals, which says if you integrate this gradient of f, so remember, any vector field that could be written as the gradient of a function was called a conservative vector field. Okay? So this is all this is basically saying is if you have a conservative vector field and you integrate, you take the line integral over C, you can compute this by simply evaluating the function at the endpoints of C. which looks awfully like the fundamental theorem of calculus. And so it seems reasonable to call it the fundamental theorem of line integrals. So this was fundamental theorem of line integrals. Let's try to prove that. Let's see, so if we want to take the line integral, nabla f dr, well, we know by the above formula how we can compute it. This is the integral from a to b. Well, we have to take the gradient of f and evaluate it at r of t. And then we have to take the dot product with the derivative. Okay, so I'm going to assume that we're working in the three variable case, just for, but everything works in the other variables the same. So in the three variable case, nabla f, right? Remember what nabla is, right? This is the gradient. The gradient of f means you take the partial derivative in each component, right? With respect to x, then with respect to y, then with respect to z. So this is the partial derivative with respect to x, and we have to evaluate it at r of t, comma the partial with respect to y at r of t, comma the partial with respect to z at r of t. And then we have to take the dot product with the derivative of r. And remember, r has component functions. Since we're in the three variable case, we can call those component functions, say, x, y, and z. So we could write here, this is x of t, y of t, z of t. And so the dot product is going to give me the derivative of x, the derivative of y, not the dot product, the derivative will give me that, and then dt. Okay, so the dot product is given by multiplying the individual components and then adding it up. So this is fx r of t times x prime of t plus fy r of t y prime of t plus fz r of t z prime of t. But this is exactly what you would get if you took the derivative of f of r of t. All right, with respect to t. It's just the chain rule. Okay, but if you take the derivative of the scalar function and then you integrate it, you take the derivative and then you integrate it. What have you done? You just get back what you started with, right? Up to a constant, but since this is a definite integral, you just evaluate at the endpoints. So the antiderivative of this is just f. So this is f of r of b minus f of r of a, which is what we wanted. Let's do a quick little corollary to this. And I think I might have mentioned this last time, but we'll write it down formally. So let's let C1 and C2 be smooth curves. And I guess I should say with the same endpoints. So let me draw a picture before I state what's going on. So you have 2 points, and I have a curve C1 and a curve C2. And if I have a function which satisfies, let's say a vector field, right, which satisfies all the hypotheses we have here, then I could compute the line integral of the vector field over C1, or I could compute the line integral of the vector field over C2. And generally speaking, when you compute the line integrals over different curves, you should expect to get different answers. Yeah? If you integrate over different intervals, don't you expect to get different answers? Yeah? Okay. So let's assume that, again, all the hypotheses of the fundamental theorem. So f is a differentiable function. On C1, C2, and the gradient of f is continuous on C1 and C2. So we can compute the line integral of the gradient of f, and we can compute the line integral over C1, and we can compute the line integral of the gradient of f over C2. And the question is, what's the relationship between them? If we know one of them, can we figure out what the other one has to be? But here's the thing. The fundamental theorem tells you that the way you compute the line integral is by taking the function and evaluating it at the endpoint. So, by the way, there's an orientation to these, right? So you start at the endpoint and you subtract at the initial point. But the initial and end points for C1 and C2 are the same. So when you compute this for C1 and C2, you get the same numbers out. Because all you're doing is evaluating the function at the end point. The function doesn't see, apparently, what's going on in the middle. It only cares about the end points. Right? This is your R of A. This is your R of B. Now you should be upset that I use R here. C1 should have like an R1 connected to it. And C2 should have an R2. But even if I do that, that's okay because at A, they should be the same, right? You should get the same points because they have the same thing here. So it doesn't matter what you call them. So I'll call this that, and then all this that. It didn't even have to be an A and a B here, really. Right? Because all that matters is what point in space it is. That's the whole point. What I call them is irrelevant. So in fact, when I compute this line integral, the line itself doesn't matter. The smooth curve doesn't matter, as long as the hypotheses are met on it. And so these are actually equal. This is really neat. So this is called path independence. And we can immediately write down another corollary from this. If C is a closed smooth curve. What's a closed curve? Closed curve is one that ends where it starts. Okay, so it looks like this. The terminal point equals the initial point. So it's closed. Okay, C is a closed smooth curve. F differentiable on C. Gradient of F continuous on C. What happens if I integrate C? What does the fundamental theorem tell you? Fundamental theorem says you have to evaluate the function f at the terminal point and the initial point and subtract the values. Yeah, the terminal point and the initial point are the same. This is actually 0. This is really weird, right? You integrate over this whole curve, and the fact that it's closed automatically means the line integral is 0. Those, of course, who are in my 481 class are not surprised to see this. In complex analysis, you have a wonderful class of functions called analytic functions. And when you integrate analytic functions over any closed contour, you always get 0 out. So there's a lot going on here that's in common. So it's not a huge surprise. Okay. Good. Okay. So I want to show you this condition. Well, this not specifically, but the condition that you're working with a conservative vector field is slightly important. That is, I want to give you a contour and find the line integral of a vector field, and then give you another contour that has the same endpoints, and then show you actually get different values. And the problem is going to be that the vector field I choose is not a conservative vector field. It's not the gradient of some function. So actually, this integral, if you look back in your notes, you'll find I'm just going to change the C on here. So let me write this help. So before we looked at the following curve. So we started at -5, -3. That was enough, I think.
She's done.
Snack time.
So what we did before is we took a line segment from -5, -3 to 0, 2. And we called that C at the time. Let's call it C1. So if you look back in your notes, you'll see this picture. we integrated, get this right, y squared dx plus x dy over this curve C1. And when we integrated it, we got 5/6. Now I remember this specifically because in the middle of the problem I said, ooh, I got it wrong. And then I thought, oh, wait a second. Actually, when I put everything together, I got the minus 5/6, and I was right. Okay. So, I want to do it again, but I want to change the contour. Not contour, well, the curve. We don't talk about contours in here. So I want to replace C1 with C2. And C2 is going to look like this. So let me give you the parameterization for it. So here, I'm going to do something a little funky. I'm going to parameterize it. Instead of in terms of t, normally we do x of t and then y of t. I'm just going to parameterize it in terms of y, because the y is the only thing that's important here. And it looks a little funny, y of y equals y, but it is what it is. X of t is just going to be, what did I say, 4 minus y squared. And the reason why I'm doing this parabola, this is just a parabola. Okay. It doesn't quite look like it because it's missing parts of it, but this is a parabola, and it's just the parabola of x equals 4 minus y squared. And so here, y, oops, that's 0. Y is going from minus 3 to 2. Okay, so this is a parameterization for this curve. And we can then turn that into a vector function. So we can write r of y equals 4 minus y squared comma y. Okay, and again, y goes between minus 3 and 2. Okay, so I would like to compute the integral over C2 of y squared dx plus x dy. So it's very nice with this parameterization. The dx is going to be very easy to write in terms of y, because I know what x is. X is 4 minus y squared, so dx is just going to be minus 2y dy. And then I know how to write dy. Dy is just dy. Okay, so let's see here. So I need to put in y squared, and the y, it's supposed to be y of r of y. Okay, but the y is still just y. So we're going to integrate minus 3 to 2 y squared, and then dx, we just said was minus 2y dy. So minus 2y dy plus, now the x becomes a 4 minus y squared. And then we need to put dy, which we put dy. Okay, we have 2 dy's, we can factor it out. And we get minus 2y cubed minus y squared plus 4 dy. And now this is just baby stuff. Okay, let's see. Minus a half y to the 4th minus a third y cubed plus 4y at minus 3 and 2. Which is, okay, we got some arithmetic here. 16 over 2 is 8, so minus 8. Minus 8 thirds plus 8. Minus, okay. Minus 3 says to the 4th is 81 over 2, so minus 81 over 2. Minus, okay, let's see. minus 3 cubed is minus 27, with another minus plus 27 divided by 3 is 9, and then minus 12. And let's see, the 8's cancel, so you have minus 8/3, and then you have plus 81 halves, and then you have minus 3 with another minus plus 3. Okay, if we put these all over 6, then you get, let's see, minus 16 plus 243 plus 18. So 18 minus 16 is 2, so 245/6. Okay. I assume I did my arithmetic correctly. Okay, so the important thing is not that they both got a 6 in the denominators. It's that one of them is negative and one is positive. Yeah, they're different. This is definitely not equal to minus 5/6, which was the integral over C1. So we don't have path independence. Why not? It's supposed to be path independent, right? Didn't we have a corollary that said that? Well, path independence is assuming that your function is the gradient of some function. That would mean you would need to find a function whose derivative with respect to x was y squared and with respect to y was x, right? Okay, you go back and see this had something to do with the curl. Right? The curl gave you a way of checking that you had a conservative vector field. And if you take the curl here, you don't get 0, which is what you're supposed to get. So that's good evidence that it's not working. Of course, this corollary now becomes a proof that you do not have a conservative vector field. What do I mean by that? It becomes a proof. I mean, the corollary says if you have a conservative vector field, and of course all the hypotheses have to be met, but they are, all of our functions are really easy. If you have a conservative vector field, then it's path independent. No? The fact that this was not path independent tells you cannot have a conservative vector field. So, if a vector field is not path independent, then it is not conservative. I.e., it is not of the form. Okay. This isn't actually a new statement by any means. It's simply the contrapositive of this corollary. If you don't have path independence, then it's not a conservative vector field. Okay. Any questions? Tyler.
So if a question asks us to compute a line integral, then you have to check answers are the same, or if they're not the same, which one should be the answer? So,
Well, these are both the answer. I mean, there is no one answer for this function, right there, for this vector field here. There's no, this is the line integral between for any path between these 2 points. It doesn't work that way. Right? It's just for conservative vector fields, there's just going to be one answer, no matter which way you go. Right? For non-conservative vector fields, you have to know which way you're going. That's why conservative vector fields are so nice. Is all you have to do is know what the endpoints are. That's why we're interested in them. But as we saw, a lot of these good vector fields that show up in physics, like the gravitational field, electric field, these things are conservative vector fields. So they will be path independent. I don't think this board's been written on in quite a while. Not erasing very much. Okay. Let's talk about Green's theorem. What's that?
That was my final project last semester.
Oh. So, when we learned the fundamental theorem of calculus, we were very, very excited because we were learning something fundamental, right? No, that's not why. It was because we didn't know how to integrate, right? We wanted to integrate, but all we had were these limit definitions. And those were not terribly helpful. You had to do Riemann sums, and we never actually even did those because they were so heinous. But it was really nice because it said if you have this definite integral, all you have to do is take antiderivatives and evaluate the endpoints. So Green's theorem is going to be very analogous to the fundamental theorem of calculus, only it's going to do things for double integrals. Right? It's going to turn something into a double integral. But unlike the fundamental theorem of calculus, this theorem is going to be more useful going both ways. Right? It was very unusual that you would say, I want to compute this function evaluated at these 2 points where I subtract them, but instead I'm going to use the fundamental theorem of calculus to express it as a definite integral. That was more rare that we did that. Green's theorem, you're going to do that quite often. Okay, so to state Green's theorem, we need one little bit of terminology, which is going to be the notion of orientation, and specifically positive orientation. So let's say I have some region. It's not really supposed to be cusped or anything. Okay, so you have some open region, and I start going around it in some direction, right? Going around the border of it. How many different ways can I go around the border? There's two. Yeah. One direction is, say, this way, and the other direction would be, well, the other way. Good. We're going to differentiate between those two directions, and this is, in some ways, a cultural choice. And we're going to call this direction, where you're going counterclockwise, positive orientation. Now, sometimes it might be a little difficult to tell if you're going clockwise or counterclockwise. If I, really started doing weird stuff, well, it's not supposed to intersect. If I started doing weird stuff, if I just gave you some point, right, so okay, this stuff's all inside here. If I gave you some point on it and said, are you, I covered up a lot of stuff and I said, okay, here's a point. Are you, as I go this way, say, am I going in the counterclockwise or clockwise direction? Okay, or even if I did it down here. You can tell these are going the same way, but it's not always quite clear. Okay. So the other rule of thumb that you can use is that, so for positive orientation, the inside is on the left. So for these points here, the inside is on the left, so this is the positive orientation if you're going this way around the curve. It may not be clear. You know, if you were right here and I said, okay, we're going to go this way, am I going positive or negative? It kind of looks like positive orientation, no, or negative orientation, but because it looks like it's going clockwise. But in fact, the inside is on the left, so this is still positive orientation. And if you follow it around, you can see, oh yeah, it does end up going back that way. Just got to follow the line.
If you're in the direction of the arrow, it's on the left. So
If you're in the direction of the arrow, it's on the left.
okay.
Yeah. So the inside is on the left. So yeah, that's based on which way you're facing. So if you think of if you're riding a bicycle and you're riding on the border of this thing, and the inside of it is pulling on you, you're going in the positive orientation if when you fall down because it pulls so hard on you that you fall to the left. Okay, that doesn't actually help anything. But I just like the idea of people falling over on bicycles, I guess.
That's horrible.
I know.
Sounds Freud.
Okay, so let's assume that you have such a curve, C, and C is, say, given by a vector function, R of t. And let's see, I think I want to, let me give a name to the inside of this, call it D. So C is the boundary, D is everything. Yeah? That is all this shaded stuff. And let's assume that you have two functions, P of xy and Q of xy. And these should have continuous partial derivatives. We've seen that sort of condition before. So we're going to assume that these have continuous partial derivatives on some open region containing D. Okay, this is kind of a technical thing, but you want to be able to put some little open set around D, and everywhere inside that open set, these functions, P and Q, should have continuous partial derivatives. Okay, it's a little technical thing that you need. Remember, open means that if you stand at a point in it, you could draw a circle around yourself that's completely within the set. You can't, say if you're on the border here, you cannot draw a circle around yourself that's completely within that set. It's not open. Okay. So those are our assumptions. Now I can tell you what Green's theorem is. So Green's theorem is going to give you a formula for integrating around the curve C by turning it into a double integral over the region D. So Green's theorem says if you integrate C over C, P dx plus Q dy. Okay, so I have these two functions, P and Q. Okay, so I'm going to integrate once with respect to x and once with respect to y. And I'm integrating them both over this curve C. And this is the same as the double integral over D. The partial derivative of Q with respect to x minus the partial derivative of P with respect to y, dA. And remember, this A is just the thing that we use when we double integrals, right? It stood for area. Notationally, let me just mention, I think I've mentioned this before, it's kind of an annoying notation. Is that, well, C is could be the boundary of this D. And so sometimes we write, for the boundary, they use the symbol that we use for the partial derivative. But this means boundary of D. So this is actually saying something very similar to the fundamental theorem of calculus. Except now it's for double integrals. Right? The double integral of some function is given by taking an integral of the original function. Here you have derivatives. Here you have the functions before they took derivatives. Right? So they're like antiderivatives. So you're going to integrate the antiderivatives along the boundary. You're evaluating this double integral by just looking at what's happening on the boundary, which is exactly what we did with single integrals. Right? Only the boundary of a line segment the boundary is just A and B. There are only 2 points to evaluate. Right? The boundary of the endpoints, not the stuff in the middle. Well, this stuff in the middle doesn't count. All that matters is the boundary. And it's exactly what happened with line integrals when we wrote down this fundamental theorem of line integrals. All that you cared about, right, is the values on the endpoints of the line segment, or the curve. What's different, as I was saying before, is you could say, okay, I want to compute this double integral by turning it into a line integral, where we just evaluate on the boundary. But actually what's more typical is you use this the other direction. You will start with a line integral, and then you're going to turn it into a double integral, and say that's going to be much easier to solve. And one of the reasons it's going to be much easier to solve is that, well, you may have to be integrating all these nasty functions P and Q, but when you differentiate, they might get much easier. Okay. And when we do a couple examples, we'll see. So I should mention the proof. Well, to prove this in its full generality is not so straightforward, and when we certainly don't have the time or patience to do it. But at least in some special cases we can do it, and it's not that hard. And so I'm going to assign it as homework. But I will give you ample hints to do so.
And so C and D correspond to the graph?
Yeah, these C and D are coming from these pictures. All those assumptions about P and Q having continuous partial derivatives on some open region containing D, all that is assumed in this theorem. Okay. So I'm going to evaluate a line integral, and I'm going to first do it just using the traditional way that we've done it, and then I'll do it using Green's theorem, and then we can see how the method changes. So first, let me tell you what my contour is going to be. So I'm going to start at 0, 0, and I'm going to end up at 1, 1. And I'm going to head there in two different ways. First, I'm going to take y equals x squared, and then I'll take x equals y squared. So if I call that C1, what I'm going to do is go up C1. And if I call this C2, I'm going to go down C2. So I'm actually going to end up where I started. So I'm going to go up and then down. Okay, this is a closed curve. Okay, so I want to compute the following integral. I'm going to label it I just for my usual technical reasons. So C is just C1 and then C2, right? You do C1 first, then you do C2. We want to integrate the function 2xy minus x squared dx plus x plus y squared dx. Now to do this, so forget about Green's theorem, we're just going to do it how we would normally want to do it. The way I can integrate this is by first integrating over C1 and then integrating over C2 and adding that together. So this is the same as the integral over C1 of that stuff plus the integral over C2 of that stuff. Okay. So to do that, I'm going to need to parameterize C1, I'm going to need to parameterize C2. Okay, but I can use this trick that I used before. Since I'm giving this curve quite explicitly, y equals x squared, I'm just going to parameterize C1 by, say, R1 of x. And it's going to be x comma x squared, where x goes from 0 to 1. Right? That completely parameterizes this curve, right? The x-coordinate can always be thought of as x, and then the y-coordinate is x squared, because it's y equals x squared. And x is going from 0 to 1. And then C2, I'm going to do that in terms of y. And that'll be y squared comma y, where y goes from 0 to 1. Well, actually, I should say, yeah, I think I might have wrote it backwards to solve that problem. Yeah, that's right. Okay, so this is actually not correct. And you know why it's not correct? The direction is wrong. This would start here and go up the curve this way, but we want to go down it this way. So this is actually the negative of C2. Okay, that's not so hard, because we know that when you traverse something backwards, right, with respect to an x or a y, ooh, this should have been a y. With respect to an x or y, it's just going to negate the integral. So, let's see here. Let's handle the C1 first. So, if we integrate over C1, 2xy minus x squared dx plus x plus y squared dy, this will equal, let's see, 0 to 1. Okay, now, all the x's I have to put x in for. Okay, that's not a big deal. All the y's I have to put x squared. So 2x squared, so it's x cubed, minus x squared. Okay, then I need dx, but, well, x is x, so dx is going to be dx. Plus, okay, y squared. Y is x squared, so it's x squared squared, which is x to the 4th. And then I need dy. Y is x squared, so dy is 2x dx. Okay, so this is the integral from 0 to 1 of 2x cubed. Now see, I have a minus x squared and a plus 2x squared. So that's plus x squared. And then I have a plus 2x to the 5th. All that dx. And I get, let's see, half x to the 4th plus a third x cubed plus a third x to the sixth, and 0 and 1. The 0 won't do anything. The 1 is just going to give me a half plus a third, which is a half plus 2/3, which is 7/6. Okay, that's part of the answer. Now what about the integral over C2? 2xy minus x squared dx plus x plus y squared dy. This should equal, well, if it was going from 0 to 1, you would go from 0 to 1, but we're going backwards. So actually, we should integrate from 1 to 0. Okay. And now, all the x's get replaced by y squareds. So we get 2y cubed minus y to the fourth. Okay, now dx, well, x is y squared, so dx is 2y dy. Plus y squared plus y squared is 2y squared dy. So let's see here. You have 4y to the fourth minus 2y to the fifth plus 2y squared dy, which is 4/5 y to the fifth minus a third y to the sixth plus 2/3 y cubed, evaluated from 1 to 0. Okay, now when I evaluated 0, nothing is going to happen. It will die. And then I have to subtract what happens at 1. So I get minus 4/5 plus 1/3 minus 2/3. So let's see, that's minus 4/5 plus a third. And let's see, that's 17/15. So minus 17/15. Whew. Okay, so this tells you that I, which remember was the complete integral over all of C, is going to be, where was our end? 7/6 and minus 17/15. So 7/6 minus 17/15. What I got? I thought I'd done something different. I think I did. Well, let's see. What do you get here? 105 minus 102 over 90. Oh, good. 3 over 90. Oh. Uh-oh. I thought I got negative 130. Oh, no, I got 130. It's good. It's all good. Okay. Phew. So that's what that integral should be, is 1/30. Okay, so there's a lot of work involved. It's not hard work, but there's a lot of work involved. Right? And I got very lucky. Why did I get very lucky? Because I did not make any arithmetic mistakes. How many arithmetic operations did I have to do in this? A lot. And on a test, of course, you get it wrong. And when you're building a bridge, you get it wrong. All right. Okay, now let's try it again. Method 2. Green's version. So, note that I'm enclosing a really nice region in here. And I'm going to call that region D. So I C went all the way around. It's a nice closed curve, and it gives me a region, which I can call D. Now, if you look back at what kind of assumptions we were making on Green's theorem, first we had positive orientation, which we do. By the way, if we had negative orientation, it wouldn't really be too bad. We would just negate the answer, and we'd be okay. In any case, we go positive orientation. P and Q. With P and Q here, there's P. There's Q. Okay. Continuous partial derivatives on some blah, blah, blah. Doesn't matter. They're polynomials. Of course, they're going to have continuous everything, right? Everything's fine there. Okay, so Green's version says that the integral over C of 2xy minus x squared dx plus x plus y squared dy equals the double integral over d of qx minus py. Well, what's qx? Let's see, there's our, remember this is our p, and this is our q. Qx is just 1. Sweet. Minus py, just 2x. Now this is a much nicer function, right? Okay, GA. Okay, now all we need to do is figure out what this region is. How, if we write it down, then, okay, let's see what happens. Well, how can you write down D? Well, what if I rewrite this as y equals the square root of x? This is the same thing, right, in that region. So D is all xy such that, we'll see, x is going from 0 to 1, and y sits above x squared and below the square root of x. This is a type X region. Looks a little strange. Usually x squared is bigger than the square root of x, but between 0 and 1 it's not. It tells us that we can rewrite our double integrals, the integral from 0 to 1, integral from x squared to root x, 1 minus 2x dy dx. Which equals, well, let's see, integral from 0 to 1, 1 minus 2x y, evaluated as x squared and root x, dx. Which is, okay, now, when I plug in root x, well, I don't like writing root x. Let me write x to the 1/2. It'll make using the power rule much easier. So when I do that, I get a root x. So an x to the 1/2 minus 2x to the 3/2. And that's when I plug in the root x. Minus, then I have to put an x squared. So I get minus x squared minus 2x cubed. Okay, so this is, let's see, so if we use the power rule next to the 1/2, add 1, you get 3/2, flip it, you get 2/3, x to the 3/2. Okay, add 1 to 3/2, you get 5/2, flip it, you get 2/5. Times 2 is 4/5, so minus 4/5 x to the 5/2. Okay, minus x squared becomes minus 1/3 x cubed. And then plus 2x cubed becomes 1/2 x to the 4th. When we evaluated 0 and 1, of course when we evaluated 0, everything dies, so we just need to evaluate at 1, and then everything is just the coefficient. So 2/3 minus 4/5 minus 1/3 plus 1/2, which is, well, let's see, 2/3 minus 1/3 is 1/3, and 1/3 plus 1/2 is 5/6. So this is 5/6 minus 4/5, and that's 25 minus 24 is 1/30. Sweet! No mistake. Notice, it's a much shorter proof, or a much shorter calculation. Now, why is it shorter. Well, for starters, when we did the line integral traditional way, we had to break it up into two different smooth curves, right? And then evaluate those integrals separately. When we did it using Green's theorem, we only had to evaluate one integral. Right? Okay, technically it was a double integral. It's somehow much easier this way. Not so bad. Let's see. Okay, we got a few minutes. Let's try one more example. Any questions on this one before I go on? Okay. So in this example, I'm going to start with a curve, and the curve is just going to be given by x squared plus y squared equals 9. It's just a circle of radius 3. And I want to integrate over this circle the rather simple function 3y minus e to the sine of x dx plus 7x plus the square root of y to the fourth plus 1 dy. Like I said, a really easy function. Okay, so of course, what we're dealing with is this curve C. So we're going positive orientation around it. But, of course, this fills in nicely, and you can get a good region D. And we can use Green's theorem to evaluate this. Now, why would we want to use Green's theorem? Well, think about what's going to have to happen to evaluate this normally. So first, okay, you write down the parameterization of a circle. That's the one that says x of t equals, in this case, 3 cosine of t, y of t equals 3 sine of t. So that's what your r of t is, 3 cosine t, comma 3 sine of t. And then you're going to have to plug those into y, and all the y's and x's. And then you have to multiply by the derivatives, which you can add even more cosines and sines. And then you're going to have to integrate that. That's a lot of junk to integrate. It's going to be bad. Let's see what happens when we use Green's theorem. If we use Green's theorem, it'll be the double integral over d of qx. Okay, so we take the derivative of, there's our q. We take the derivative with respect to x. No, we're using Green's theorem, which qx minus py. It's just 7. This whole nasty term goes completely away.
So you don't have to parameterize if you're doing Green's theorem at all?
I mean, the parameterization is replaced by having to write down what the region is. So that's the trade-off. But what a nice trade-off it is. This goes to 7 minus, now we need to do this with respect to y. 3. What's that?
You get a kick out of this. Like,
well, you got to admit, this looks pretty badass. Because you don't even have to compute this thing. You just have to think for a second.
Pi squared.
Yeah, well,
Pi r squared.
yeah, pi r squared, of course, what's r?
3.
3, so it's just, this thing is 9 pi times 4 is 36 pi.
Answer?
The reason he's so excited is because he's been thinking about this ever since we started integrals and complex.
Oh, yeah.
So what, 2 months? This has been in the back of your head?
By the way, if you're not seeing why this is, remember if you do the double integral and you put 1 here, then all you're doing is computing the area of this region. Because you think, okay, this is a region, and at every point I just put 1, so it's giving me a volume, really, but it's equal to the area. And of course, the area of D is just pi times the radius squared. And since the radius is 3, it's pi times 9. And you get this extra 4. Green's theorem makes really short work of this. I mean, all this, and it's just brilliant. All this nastiness that you put in here, just gone. You didn't have to deal with any of it. And that's really something.
Should we never see it? Thank you.
Yeah. I have just a little appendix that I put into my notes in case we have time. When we have time, I think I don't want to do it.
I like the purple circles.
Okay. Why don't we stop there?
Figure out why in the last one.
So tomorrow
Yeah, you did it.
we will show how to mix up Green's theorem with the curl and the divergence of a vector field. So we're going to be able to rewrite the formula for Green's theorem, but with curl involved. And also with divergence involved. So we'll have to talk about things like the tangent vector field and the normal vector field, which we haven't talked about too much. I think we had something about the tangent vector field on the homework. It was this big T.
Did you figure it out?
I don't remember.
Okay. Well, enjoy. See you tomorrow.
Okay.